Welcome to the 20th lecture on computational mathematics with SageMath. In this lecture, we shall look at some applications of derivative. So, in the last lecture, we looked at finding derivatives, including implicit derivatives. We also looked at Taylor's theorem and Lagrange mean value theorem and its geometric meaning. So, I had asked in that lecture you to look at the Cauchy-Mean value theorem and look at what is its geometric meaning. So, before we look at some applications, let us look at Cauchy-Mean value theorem. So, Cauchy-Mean value theorem actually says that if you have two functions f and g defined on closed and bounded interval a b, which is continuous on this interval and are differentiable in open interval a b, and let us also assume that derivative of g does not vanish in the open interval a b, and the end point value of g are not equal. In this case, one can find a point c in the interval a b such that f b minus f a upon g b minus g a is equal to f dash c upon g dash c. If you notice, g dash c is in the denominator, and that is why we need the condition g dash c non-zero. And in this case, actually if you look at g x equal to x, then what will you get on the left hand side denominator? It is nothing but b minus a. On the right hand side, it will be f dash c. So, that is nothing but Lagrange mean value theorem. So, you can think of Lagrange mean value theorem as a particular case of Cauchy mean value theorem. Now, what is geometric meaning of this? So, let us look at a problem and let us try to verify this Cauchy mean value theorem for that problem, and then we will see what is the geometric meaning. So, consider two functions f t and g t. F t is t cos t and g t is t sin t, t varying between 0 and let us say 3. Okay. Now, so in this case, let us take t between 1 and 10. We can just increase the range. Now, let us define t as a variable f t and g t, and a b are the endpoints. So, that is 1 and 10. Let us plot the curve and the chord joining a comma joining f a g a and f g a sorry f b g b. So, this point is the we are taking a curve which is parametric defined, and this is x coordinate is t cos t, y coordinate is t sin t. So, this point will be f a comma g a, and this point will be f b comma g b. So, you are looking at this chord join these two endpoints. So, that is the chord. Now, Lagrange mean this Cauchy mean value theorem, what it says is that there exists a point strictly between a and b at which the tangent to this curve is parallel to this chord. That is what it means. So, you can imagine geometrically there could be one point here at which this the tangent to this curve will be parallel to this. There will be another point somewhere here at which the tangent will be parallel to this chord. So, that is the geometric meaning of Cauchy mean value theorem. Let us try to verify that. So, in order to verify, let us first define the derivative of f and g. So, derivative of f we will define in f1 and derivative of g we will call as g1, and then let us take m as the left hand side in the Cauchy mean value theorem, that is f b minus f a divided by g b minus g a. One can think of this as just 1 upon m will be the slope of this chord. 1 upon m will be slope of this chord. Now, then what we are looking at? We are looking at finding c such that f dash upon g dash c is equal to this m. So, we can define a function h t is equal to derivative of f at t divided by derivative of g at t minus m, and then to find such a c, all we need to do is find zeros of h t. So, let us plot the graph of h t. So, this is the slope 1 upon the slope of the chord, and let us plot the graph of h t, and this, when you plot this graph, it clearly says that the h t will have 0 between 2 and 4, 1 between 4 and 6, 1 between 8 and 10. So, let us find these zeros using find underscore root command. So, h dot find underscore root between 2 and 4, that is C1, h dot find root between 5 and 6, that is C2, and h dot find underscore root between 8 and 10, that I have stored in C3. So, let us look at what are the values of C1, C2, C3. So, C1, C2, C3 are these values, and that you can see is that all these values lie between A and strictly between A and B. Now, let us try to plot graph of the tangent to these curves, and then see whether that is parallel to the chord. Okay. So, here we are defining the tangent at the point f c1 g c1, and this is the plotting that tangent in green color. Similarly, this is the point P1, that is f c1 g c1. Similarly, define the second tangent and plot that second tangent, and then plot also the second point, and add all these things to the given curve which we have plotted earlier along with the chord. That is what we are doing. Third point I am not adding here because there are third point also. So, one can add that third point as well. So, just let us look at with these 2 points. So, if you run this, you can see here there are these 2 points green. One is the C1 actually, f C1 g C1, and this black one is j f C2 g C2, and the tangent at these point are parallel to this given chord. And here the slope of this tangent will be actually 1 upon m, which we have defined, that is same as saying g1 g dash at C1 divided by f dash at C1. Okay. So, that is how it is plotted. You can add the third point, you can expect third tangent to be somewhere here. So, this is verification of Cauchy-Mean value theorem and its geometric meaning, right. Now, let us look at how to find local maximum and local minimum of a function, that is an application to derivative. Okay. So, I am sure all of you know how to find local maximum, local minimum using first and second derivative test. Okay. So, let us take an example. Suppose you have a function e to the power minus x by 2 plus e to the power minus 2 x square, and suppose for this we want to find local maximum and local minimum in let us say either in some interval or entire line. So, let us first plot graph of this function. So, graph of this function, this is how it looks like, and what is happening is this if you go to x minus infinity, this will keep on increasing. So, you cannot have any local maximum, local minimum, and on the right hand side again it will keep on decreasing and it will go to 0. So, it seems that it has two critical points where that tangent is parallel to x axis. One of them is here, other one is here, and there will be some actually point of inflection where the curve changes the concavity or convexity, right. So, that is the, so in case we want to find out local maximum, local minimum, of course, you can find derivative, equate it to 0, find those critical points, and then find second derivative and check whether the second derivative is positive or negative at that point. But let us use inbuilt function first. So, the Sage has an inbuilt function called find underscore local maximum, and in this case we see that there is a local maximum between minus 1 and 1. So, if I execute this, it will give me two values. One, the first value is the value of the function, that is the maximum value, and this is the point at which the local maximum occurs. So, this points numerically, that is why you can save these numbers in decimal. Similarly, if I want to find local minimum, then you have to mention the interval. So, in this case I have mentioned minus 1.5 to 0.5, and if you find this, you will see that the local minimum occurs at minus 0.86694 and so on, and this is the minimum value of the function, right. So, Sage has inbuilt function to find this local maximum, local minimum. Of course, in case you mention some interval in which it does not have a local maximum or local minimum, but it will find maximum minimum of the function at that point. So, for example, if I look at find local minimum between, let us say, 1 and 2. So, by looking at the graph, you can see here that the minimum will lie at 2 and the maximum will be at 1. So, that is what you will see numerically. So, for example, the minimum value is at 1.999, which is very close to 2, and this is the minimum value. Similarly, if I ask for what is the maximum value, then you will see the maximum value lies at 1. So, let us say f dot find local maximum between 1 and 2. This will give you the maximum lies at 1.00, and this is the maximum value. So, this will always find maximum or minimum, though it may not be local maximum or local minimum. It may not be the point may not be critical point, right. So, now if you try to kind of find the derivative of f and then equate it to 0, then you will in this case again the finding derivative, you have to use the finding derivative equating it to 0, you may have to use this find root to find the numerical root. So, this is the first point, critical point, where the derivative is 0, that is the negative of 0.866, at this is the point of local maximum, and just a second. So, this is f of x, just let me run once again. Yeah. So, if you try to plot graph of this derivative of this function, you see that it has a 1 0 at minus 1, 1 and 1 0 between minus 0.5 and 0.5. So, these are the two critical points. These are the two critical points, and to the left of this point, the function is derivative is negative. That means function will be increasing. Between this and this, the derivative is positive. So, function is increasing again between this, and after that this is all negative. So, function is decreasing. That is what you can also explain from this. So, if you find critical points, the first critical point is this, and then second critical point between minus 0.5 and 0, that is the second critical point, which was local maximum, and then let us find the second derivative at these points. So, you can see here that at second derivative at this point, the first point is positive. So, that point is local minimum, and the second derivative at this point is negative. So, this point C2 will be point of local maximum. That is what you see from the graph, right. So, this is how you can find local maximum, local minimum, and in case you have to find absolute maximum or minimum, you also need to evaluate the function value at end points along with this local maximum, local minimum, and then compare all these, and then you can find global maximum, right. Next, let us look at one more problem. This is a problem fx, consider a function fx equal to 2x cube minus 9x square plus 12x minus 3, and try to find interval on which this function is increasing or decreasing. So, already we saw this in previous example. Find the local maximum, local minimum of f, find the interval of concavity and the inflection point. So, again these steps are very similar to what we have done earlier. So, I will run this and then show you. So, this is the graph of this function, and you can see here there is one point at local maximum, this is one local minimum, and the function increases from here to here, then starts decreasing and then starts increasing from here to here, and somewhere here there will be one point of inflection, right. So, we will try to locate all these things. So, first let us find the first two derivative, call it f1 and d2f1, d2f, df and d2f, and then let us find these critical points. So, solve this derivative equal to 0 for x, and I am using this option solution dictionary, so that it will give me solution in dictionary. So, it says that there are two critical points, x equal to 1 and x equal to 2, that is what you can see from the graph. Now, let us store these critical points in A and B. So, that is the advantage of using dictionary, so that we can very easily extract the values, right. And then also find the point of inflection, that is the points at which second derivative vanishes. So, solve the second derivative equal to 0, and in this case there is only one point, which is x equal to 3 by 2. So, this point let me call as a C. So, let us store this point of inflection in C, and then let us plot all these things together. So, when we plot all these things together, this is how so we have plotted the curve, that is in blue in color, and these are the three points. Red one is local maximum, green one is local minimum, and this black one is point of inflection, and this red color curve is the curve the graph of derivative, and you can see here it vanishes at 1 and 2, and those are the local maximum, local maximum minimum points. And also this black line is the second derivative, which you can see here. To the left of 1.5 it is negative, and to the right of 1.5 it is positive. So, that is the point at which the function changes its concavity, that is okay. And also the second derivative, the first derivative is negative from minus infinity to 1. So, that in when the function is increasing from 1 to 2, the function is first derivative is negative. So, the function is decreasing, and after 2 it is positive, therefore, function is increasing. So, that is this connects all these notion of finding interval in which function increases, decreases, interval or the point at which the function changes its nature of concavity. All these things are explained through this particular example. Okay. Now, you can of course as an exercise you can find local maximum, local minimum of f x is equal to x to the power 4 into e to the power minus x. Let us look at another example. So, this is an example to find in which we want to show that in this curve y equal to 1 plus x divided by 1 plus x square has 3 points of inflection, and they all lie on a single straight line, on a same straight line. So, that is quite easy actually. You need to find the critical points, and at these critical points you join the line and then see whether they lie on the same critical along the same line. Right. So, let me run this, define f x, define derivative, and then find out the critical points. These are the two critical points in this case, and let us store these critical points in A and B, and let us find out the point of inflection, that is equate second derivative equal to 0. So, you can see here there are three points of inflection here. One is at minus 2 minus square root 3, other one is square root 3 minus 2, and the third one is at 1. So, again let us just store this in C1, C2, C3, and then plot graph of the function along with all these inflection point, and then join the line joining C1 FC1 and C2 FC3, and then see whether the second point also lies within this. So, that is what you can see here. So, this is your C1 FC1, this is C2 C3 FC3, and this is C2 FC2, and that all these 3 points are along the same curve. You as an exercise you should also try to find out point of local maximum, local minimum in this case as well, that you take as a practice exercise. Okay. Next let us look at, for example, this function f x equal to 1 plus 40 x cube minus 3 x to the power 5, and look at the tangent and check at what point this tangent have highest slope, largest slope. So, how do we do that? So, first let us find the define the function, find the derivative, first derivative, second derivative. Let us plot the graph of this function, plot of the graph of this df, and this is the derivative. So, the point at which it has highest slope is, that is the point at which the function, the derivative has is maximum, and these are the 2 points you can see here. This is one point, this is another point. So, you can simply find the derivative of find the local maximum, local minimum of derivative of f. So, you have to find out second derivative equal to 0, that that will be critical points of derivative of f, and these are the 3 points actually, but at 0 it has local minimum. So, if I try to find the local maximum between let us say -5 and 0, that is the point. At -2 it has close to -2 it has local maximum, and you can check the second derivative, it will be positive. Similar with second derivative will be negative, that is why point of local maximum. Similarly, you can find another local maximum at 2.00, right. So, these are the 2 points at which this function tangent has maximum slope, right. Okay. So, let us look at one problem as an application. This problem is taken from James Stewart book on calculus, early transcendent, 8th edition, and the problem is as follows. The Hubble Space Telescope was deployed on April 24, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from lift off at t equal to 0 until the solid rocket booster were jetoned at time 126 second is given by this particular equation, and then this is in feet per second, the velocity. Using this model, estimate the absolute maximum and absolute minimum value of the acceleration of the shuttle between the lift off point and jettisoning of the booster. Okay. So, this is quite easy actually, but this is an application in physics in rocket launching. So, if you want to find the acceleration, this is the velocity. Acceleration is nothing but rate of change of velocity. So, all we need to do is find the derivative of v and find the local maximum, local minimum of that, right. So, let us define this function v. Let us plot its graph. So, the graph of the velocity looks like this. So, you can see here, this is not a straight line, it is going like this. So, let us now find out what will be the derivative of the velocity that I have stored in a, that is acceleration, and if you try to plot graph of this acceleration, this is how it looks like. So, you can see here there is one somewhere local minimum somewhere here, and then it keeps on increasing, right, at 126 till 126 second. And if you try to find the local minimum of this acceleration, that is at about 23.1157 second, and the other one at the end points we need to compare what is the acceleration. So, at 0 the acceleration is acceleration at 0 is 23.61, and at 23.11 second it is 21, and here it is 62. So, the acceleration is minimum at 22.52.28 second, maximum at 120 second, at 62 at 126 seconds, and the maximum acceleration is this. So, that is a very easy problem. Okay. Now, let us look at one more problem as an application. This is again taken from this James Stewart calculus book. So, this is regarding the planes and birds minimizing energy when they fly. So, the first problem in this is power needed to propel an airplane forward at velocity v is given by this. So, this is the power, this is a function of v, where a and b are constants, a and b are positive constants specific to the particular aircraft, L is the lift and upward force supporting the weight of the plane. Then you have to find the speed that minimizes the required power. So, you have to minimize p for v. So, let us define this all these variables a, b, L and v, and define this power function as a function of p, and then let us find the derivative. So, the derivative of this looks like this, and then we find the derivative equal to 0 and solve for this v, and in this case you can see here that there are 4 roots, but then 3 of them are imaginary, only the third root is only the fourth root is real. So, that is the point at which this power is minimum, that is the velocity at which this power is minimum. So, let us store this, let me show you. So, this is the point, this is the velocity at which the power is minimum. Okay. Next, let us look at the speed found in the problem 1 minimizes the power, but a faster speed might be use less fuel. The energy needed to propel the airplane a unit distance is given by E, the energy is given by P upon power upon the velocity. Then at what speed is the energy minimum, right? So, that is again let us define the E as PV upon V, and then find its derivative and equate it to 0. So, that is the derivative equated to 0, and then solve for the velocity v, and then again it has a single real root, that is the velocity at which this energy is minimum, right. So, this is the velocity at which the energy required is minimum. The third problem is how much faster is the speed of the minimum energy than the speed of the minimum power. So, we have already computed these two things. So, we will just take the ratio of minimum power divided by minimum energy, and it says that the ratio is this 3 into 1 by 3 to the power 3 by 4. Okay. The fourth problem in this is, suppose this we apply to bird flight, and in this case the term a v cube is split into two parts, a b v cube and a w v cube. So, a b v cube is the bird's body and a w v cube is bird's wing, and suppose x is the fraction of the flying time spent in flapping mode, that is in the big wing flapping, and if m is the bird's mass and all the lift occurs during the flapping, that is the assumption, then the lift is given by mg upon x, where g is the acceleration due to gravity. So, the power needed during this flapping will be given by Pf is equal to ab plus w into v cube plus b into mg by x whole square upon v, and then the power while wings are folded is, let us say, P0, which is AB VQ, and then you have to find the average power over an entire flight cycle. So, average power PA will be x times the PF, that is during the flapping, and this 1 minus x naught during this folded one. So, this is given by this, that is just expression. And then now the question is, for what values of x the average power is minimum, and so let us find out. So, again let us denote this average power, this Pf is equal to this is the Pf which we have defined earlier, and next we defined P0. So, that is ABVQ, and then let us take the average power as Pa into P is equal to x into Pf plus 1 minus x into P0. So, that is the average power, and then let us find the derivative of average power dPa, and solve this equal to solve the derivative equal to 0 for x. So, that is again it has two roots, but one is negative, which is not possible. So, the positive root is given by this. So, that is the x at which this this average power is minimum, right. And you can see here this is proportional to 1 upon v square. So, as the velocity increases, this x will decrease, right. So, that is the observation, right. And next let us look at the average energy over a cycle A is given by the P A upon V. P A is the average power. Then for what value of x this is minimized. So, again we can just define E A and then find the derivative of E A equated to 0 and then solve for this. Again it gives me two values, but only one is minimum, one is the positive, and that is the point which is equal to this. This is exactly same as what you got for minimum minimum value of power of average power in terms of x, right. So, these are the some applications of derivative, and you can look at more applications solving these problems of minimum, maximum, etc. basically is very easy in SageMath. Whenever you are unable to find the closed form of the critical points, you can use this numerical local maximum, local minimum, that is find underscore local maximum, local minimum. Similarly, to compute the critical points, you need to use find root function, but first you need to plot the graph of this function. Okay. So, let me stop here. Thank you very much. Next time we will look at finding integrals in SageMath.